My name is Adolfo Jasso Campos, and today we'll explain the experiment of the 2D interference. So, when a wave, as we saw previously, a wave can interfere with itself, and there is no difference in two dimensions. Here on the left is a simulation of interference of two sources of water, creating ripples on the water surface, creating that 2D interference. This simulation is on this link right here, which will also be in the description of this video. For the experiment, we're going to use these formulas, more specifically the one for disruptive interference, in order to see if the simulation is accurate to the theoretical formulas and how exactly this affects the look of the waves. Okay, so here on the left we have an example of the interference we're going to get, and these lines in red are the nodal points of this interference pattern, and on green they are the interference pattern for the antinodal lines. On the green ones, the formula is this one right here, which is for the disruptive criticism. We're going to use this for the experiment. We're going to calculate the distance between this line right here and this line right here, which will eventually get us to d times sine of theta. And as these are the first antinodal lines, m in this case will be equal to 0. So therefore our wavelength will be equal to 2 times d times sine of theta. Okay, so here is the process for how we're going to get to that point. First of all, for all the simulations we're going to make, the separation will always be 3 centimeters, which is this value of d right here. Then, the distance I said we're going to measure from antinodal line to antinodal line is 2 times y. Y will be the distance from the center to an antinodal line. So therefore we need to divide it by 2. The uncertainty for y will be just the uncertainty for 2y divided by 2. Then we need to get d. D is the distance from the source, which will be this right here, to the point we're measuring, which will be this one right here. This distance is d. It's not exactly from the source, it just has to be on this line from the source. Okay, so that's what's going to be d. Now, y over d is actually the tangent of theta. So therefore, to get theta, we can simply use the arctangent of this formula. But for the uncertainty of y over d, we're going to use the formula for uncertainty of division, which says that the uncertainty of the result will be equal to the square root of the uncertainty for the value in the numerator, in this case y, divided by the value in the denominator squared, plus minus the uncertainty for the denominator, which in this case is d, times the numerator divided by the denominator squared, and all of this squared. Okay, so then we're going to apply this formula right here. And for the uncertainty, we're going to use this formula right here, which says that the uncertainty for the result will be equal to the absolute value, the uncertainty of the value we use for the operation, divided by 1 plus x squared. This is because the derivative for arctangent is 1 divided by 1 plus x squared. Then, now with the have theta, we can just take the sine of that. So the derivative will be this right here, because the derivative of sine of x is cosine of x. The uncertainty will simply be the uncertainty of x times cosine of x. Now that we have the sine, we will multiply by d, which remember is of 3 centimeters. And once we have that, we can simply use this formula. Remember, we got that wavelength will be equal to 2 times the sine of theta. So therefore, the theoretical value of the wavelength will be equal to this one. Now we also get the experimental value of the wavelength. This will be measured by just let me show you here. We can in the simulation turn on just one faucet, and this will produce a wave without interference. We can measure the wavelength of that, and that will be our experimental wave. For the uncertainty of multiplication, because we multiply phi times sine of theta, is the square root of the uncertainty on x times y squared minus the uncertainty y times x squared. This is how we will get all the uncertainties. For example, is this step right here. Okay, so here is what I told you about the way we get the experimental one. And here is actually the image for our first simulation. In this case, the frequency is at its maximum possible simulation. As you can see, here we can see 5 antinodal lines, which are red, and 4 nodal lines, which are green. Now, we use these two tools the simulation gives us. The first one tells us the difference between 2 points in the waves, in this case the water waves. As you can see here, both points are on 0, so therefore these are 2 points of antinodal lines. And the distance is 5.3 centimeters. This is too wide in our calculations. We also need to get D, which was 9.5 centimeters. And with these two values, we can actually calculate the whole way down, as I told you, and we eventually end up that the theoretical wavelength is 0.016 meters, or 1.6 centimeters. Now, when we get the experimental one, we get that it's actually 1.7 centimeters. So therefore, they are really close. The error was just 0.00088 meters, around 5.5%. But as these uncertainties are somewhat large, by millimeter, they can actually be covered by the error propagation. If we got a more accurate measuring of distance, maybe we'll have gotten a lower error. But here is our second try, our second simulation. Here the frequency was half the previous one. As you can see, there are only 3 antinodal lines and 2 nodal lines. This is half of what we saw before. This is because the speed of the wave on both simulations is the same, and the speed is dependent on the wavelength and the frequency. And as we change the frequency, the wavelength has to adjust itself. So therefore, this means that not only it will look different, the image, but it will also affect the results for the wavelength itself. You will see how we get. So here is the same tools we used. Now the distance between the 2 antinodal lines was of 8 centimeters. This is the y. Remember, we also need d, which was 8.5 centimeters from the point we measured. So therefore, we get all these calculations, and by the end, we get a theoretical value of lambda 0.026 meters, around 2.6 centimeters. Now we get the experimental one. We get the actually 2.7 centimeters. Here on the graph, you can see the 2 points we got are not exactly the same, but this is because as the wave travels, it takes into account the energy dissipated. You know? So in the real life, as the wave spreads, the actual water level, which is what is measuring here, will be lower the further you go from the source. And just reflected here. These were the two points. We get the highest peak, which will be the wavelength. Remember, wavelength can be measured if we assume this equal to the water level between peak to peak. This will be the wavelength. As you can see, they are the same for both points, so therefore this is the experimental wavelength. We also got a very small error of around 0.0015 meters, around 5.7%, which is about the same as the last one. So we can say that the simulation is accurate to the theoretical values. Maybe it's more accurate than it shows here because the uncertainties for the measurements of the distance are too big, but it could also be higher. Last, I want to compare the two simulations we got. Remember the first one, which is on the left, has double the antinodal lines. Sorry, the nodal lines compared to the second one, which was half the frequency. This is also reflected on the values we got for the wavelengths. Remember, for the second one was 0.027, and for the first one was 0.017. This is a big difference. This is because, as I told you before, as the velocity of the wave depends, well, you can say it's related to the frequency and the wavelength. When we change the frequency that much, by half, we also change a lot of the wavelength. So now that the wavelength is, in this case, larger, it needs more space in order to interfere with itself. So therefore, we have on the same area on both simulations, as you can see here, is the scale, and it's about the same. We don't see as much of the interference on the one on the right, which has a lower frequency. If we extend the image, we will see a very similar image to the left, but it will be on different scales. So that's why they look different. So thank you for watching.